Okay, hello everyone. Glad to be back. So today we're going to finish up this unit on convolutional deep networks, and I just wanted to go through quickly a few of the slides that were posted on YouTube only, just to see if you guys have any questions about anything. So just to start, I just wanted to point out the overall structure of these convolutional nets. And a few people have asked me, when you build these networks, how do you choose the number of nodes in the different layers? And my answer is that there's no optimal strategy for that. It's something that people do by trial and error, but you can notice some trends by looking at what other people have done. So just for AlexNet, if you count up the total number of elements in the feature map, so in the first layer we have 224 by 224 by 3. That's 150,000. The next we have 55 by 55 by 96. That's approximately twice. Then you have 27 by 27 by 256, about 190, and so on. So you can see that the overall shape of the tensors it's increasing a little bit and then gradually decreasing. And finally, of course, we have to get down to 1,000, which is the number of classes. So this is just an example of how AlexNet did it, but just an example. Another thing, kind of at a very high level, that we always have to do in these classification networks is we're starting with something of the shape of an image. So pixels by channels. Channels could be 1 for grayscale, 3 for color. And we eventually have to convert to 1,000 channels if we have 1,000 classes. So overall, we need to transition the shape of the feature map or the tensor, from this to this. And so gradually, we reduce the number of pixels using either downsampling or max pooling or average pooling, and we gradually grow the number of channels until we get 1,000. And as I think you saw in the last YouTube video, there's various other details other strategies that we can use, other tricks that we can use in designing these networks, but they have sort of a similar form at a high level. Any questions on architectural stuff? Okay. So another important equation is this one. This is what convolutional layers do. So I know sometimes this is a little confusing to students. So you can kind of think about it as a combination of matrix multiplication and convolution. So if you imagine that the kernel W has only 1 pixel. So that would be sort of a trivial kernel, but if it has 1 pixel, then that would mean the capital K's are 1, which means that the little k's are always 0. So this becomes 0, this becomes 0. Because the little k's are 0, these go away. And if you look at the remaining equation there, you see that it's just matrix multiplication at every pixel index. So J1 and J2 are the pixel indices, and there's just a matrix multiplication done at every pixel, right? You're just doing a matrix multiplication across the input channels to get you the output channels. So that's the case where you have just 1 pixel. On the other hand, if you focus on the case of a single input and output channel, then you can sort of ignore these indices, and then you just have plain convolution. So what you have in the end is a combination of convolution spatially and matrix multiplication across channels. So that's what these layers do. Okay, anything I can clarify about convolutional layers. Do they sort of make sense? There is some visualizations on this webpage. Some former students from this class told me about those visualizations, and they said that they helped them, so I linked them there. The reason we do convolution and not dense multiplication is because it's much, much simpler. In this example, it saves many orders of magnitude in terms of weights and therefore in terms of training time and memory and all that. We couldn't really do this without, doing things with just dense layers, it just wouldn't work. Let's see. Then there's a bunch of stuff about implementation. And then I think there was a discussion about backpropagation. It's really pretty similar. I'll just point out one thing. I'm not sure. I don't remember if I covered it in the lecture notes, but did I explain this equation? Because this one is a little... So here, we want to do DZLDA, DZDA. So for that, we have this equation. But the problem is we want to know what is the influence of a particular activation. So activation, let's say, at pixel location K1 and K2. But the way this equation is written, it's hard to see what that's going to be because we have a sum in each of those indices. So what we do is we have to just rewrite this equation using slightly different variables so that we express this in the form we want. So in particular, what we can do is we can come up with some new variables. Let me just call it P1 and P2. And in this case, so we're going to get rid of the K variable. So you can see that, let's see. K1 is going to be P1 minus J1. K2 is P2 minus J2. And so what I can do is I can replace these variables here and then replace these sums with P1, P2, and then I'm also going to have to adjust the limits of the summations. But it can be done, right? And so once you have it written that way, it's written in terms of this A quantity, how we like to see it. And now we can easily do the derivative with respect to that term, and we will get something of this form over here. Now you can see where this minus J stuff is coming from. Okay. So I think that shows up on the homework for Unit 9. Any questions on that? Okay. We talked about a bunch of tricks that are used for training. Are there any questions about any of these? No? Okay. And the last thing in the YouTube video was, and then talked about a bunch of different famous classification networks, mainly as a way of understanding how the field evolved, how different tricks were introduced, why, what the effects were. And the very last thing on the YouTube video was going through the PyTorch code, which showed how you can load in one of these pre-trained models. So for this, you use the torchvision.models package, and now we're going to load VGG16. We want the pre-trained weights, and if you do print string model, it shows you all the details of that network. And the network is basically structured into 3 parts, or maybe 2 parts and a sort of a glue piece. The first part contains the convolutional layers. The last part contains the dense layers. It's called the classifier section. And then there's a middle part that adjusts the size so that you can use this network with any image size you like. Because of the size of the image you put in will eventually determine the size of the last convolutional layer output, right? But the classifier section needs to have a fixed number of neurons because you have to, this thing has 25,088 input features. It's not flexible at all. So if you put in a different size image, this average pooling layer is the one that resizes things just to the right size for this classifier layer. And it basically either expands or averages so that it's the right size. Okay. And so now we can continue with this demo. So what we can do is we can download some images from the internet. A really nice place to do that is Flickr, photo hosting site. You have to get some API keys in order to interact with Flickr. Once you have that working, you can download images based on keywords like elephants. If you say elephants, you can just download tons of elephant images. And so what we did in this demo is we have separate test and train directories. And let's see. So we can go through all the PyTorch stuff about creating a dataset object from the data we downloaded. We can use the data loader to draw mini batches. And there are a few things that you have to do, or you're encouraged to do if you work with a pre-trained ImageNet classifier, because there's certain things that the people who designed those networks did, and if you don't do things the same way, it won't work as well. So one of the things that they did is they normalized the the color channels in a particular way. So they normalized the data so that it has particular means and standard deviations for red, green, and blue. And so that is one of the things we're going to do in the data loader so that it's sort of matched to how the network was trained. Another thing we're going to do in this case is we're going to crop to a desired size. We're going to use 224 by 224 because that was what was done for ImageNet, although you could modify the code here and you could use a different size, it would work fine. Yeah, those are the main things we're doing. And then once we have that working, you can draw samples from the data loader like this. It will draw elephant samples, and we can put them through our network. So we're just going to take these samples and put them through this pre-trained network. So some of the ImageNet classes are already elephant classes, so we don't have to retrain anything. We start by putting the model into evaluation mode. Basically, there's like a training mode and evaluation mode, so we want to be in evaluation mode so that we're not back-propagating gradients and all that stuff. It would work okay, it's just unnecessary computation. And so then you also do this with Torch Nograd, so the following things here. So actually, this is the part that prevents gradients from flowing, and then model eval, it's sort of a switch that affects other things like batch norm. it puts batch norm in the testing mode instead of the training mode. Anyway, so what we're going to do here is we take our image X, we put it through our model, and get our output. Now our output is, for this network, it's just a vector of 1,000 real numbers, scores. So we're going to convert them to probabilities by putting them through a softmax. And now we have a vector of probabilities. And then we can extract the top 3 of those probabilities using this top K command here. And we're going to choose 3. So it's going to allow us to find the indices of the top 3 probabilities in that vector, as well as the values. And we're going to use that and create a pandas data frame to show the results. So as we go down here, these are our test images. There's 10 of them. And these are the first, second, and third best guesses the network has. So here you can see probability 0 is, with 70% probability, it thought that this was an African elephant. With about 28, thought it was a tusker. With about 1.8, it thought it was an Indian elephant. And so on. Did this for all the classes, and if you look over this, you can see that all these samples were correctly classified as one of these 3 types of elephants. So it didn't make a mistake and think that one of these samples was a non-elephant. Okay, actually I think this shouldn't, that last bullet shouldn't be there. Okay, so now another thing we can do is we can take a peek inside this network and we can plot the feature maps that you see inside the network. So to do this, we can build something called a feature extractor. The feature extractor is going to take in the model that we're working with. In this case, it's this VGG. It's going to take in the particular feature layers that we want to look at. This is just going to be a list of integers, and also a list of the classification layers we want to look at. Okay, so the init part is, of course, what we run when we instantiate the model or instantiate this class. And so all it's going to do is load in these 3 inputs. And then the forward part of this class, what it does is it initializes these empty lists, and then it goes through the feature modules one by one. And so you see there's a for loop for name module in model features modules items. So this is the overall VGG in this case. Features is that first list of all the convolutional layers, and this goes through them one by one. And so this line will put X through the first layer in that list of convolutional layers. Well, it's convolution plus activation plus maybe, max pooling or something like that. And then if that particular module is in the list of feature layers, then we're going to save X. We're going to save that, and we can plot it later. And then we're going to go through again, go through the next module within the network. If that's one we want to save, then we append it to our list and so on. So we do that until we've gone through all the convolutional layers. Then we go through the average pooling layer, and finally we go through the classifier layers, the dense layers. We do the same thing. We put it through the layer, and then if it's something we want to save, we append it to the list of classifier outputs. Okay, so now we can do that in this VGG network, and we can take a peek at what it was seeing inside the network. So these are the RGB input channels. So you can see it's the head of an elephant. And the activations in layer 1, now there's, trying trying to remember how many there are. There's, I think, 96 of them. We can only show a few here, so I'm just showing 4. And you can see that they all have, they're all sort of, they have the same kind of structure as the input image. However, they have been filtered by some small kernel. I think, what was it, 11 by 11, I think, in VGG. And so depending on how that kernel was constructed, like this kernel seems to have kind of made things look like vertical edges almost. Well, you can see how the different kernels have affected things differently. So those are just some examples of what happens at layer 1. Now if you go through and you get to layer 10, you can see that things look quite differently. So first of all, the feature maps are much smaller in size. There's a lot more channels, maybe 256, I can't quite remember. And at this point, they look nothing like the original image, right? The meaning of these things is they're not really like images anymore. They're something between images and some information useful for classification. Okay, so that's just showing how you can look inside a network. All right, any questions on any of this stuff? Okay, so that sort of finishes up our discussions about classification networks, and now we're going to just quickly talk about some other topics beyond image classification. I won't get to spend much time on, but the point is for you to be aware that image classification is just one very specific thing you can do with deep networks, one of thousands of different things you can do. Okay, so if we focus on imaging problems, still a very specific thing we can do with deep networks. There's many, many different things we can do with, with images. So let me give you an example of some based on this picture here. So what we have focused on this whole time is classification. So in classification, the assumption is that for this entire image, there's a single label, cat, right? Even though when you look at the image, you see that there's actually more than a cat in the image, but that's the data set. It just has that label cat, and the task is to predict cat. We also briefly talked about this, classification plus localization, where so still this image just has one label cat, but it also has extra information that says the cat is located in this bounding box. So that information would be present in the training data, and it would also determine the task of the network you're designing. You are designing a network that, number one, predicts what is the label associated with this image, and number two, says where within the image, where do I look in the image to know that the image is that label? So that's another thing you can do. You can go further. You can take that idea further into what's called object detection. In object detection, it's similar to this, except you can have more than a single label per image. So here, this object detector has said there's a dog, another dog, and a cat in this image, and it has drawn bounding boxes around each one. So this is object detection. Then there's another variation called instance segmentation, which is similar to object detection, but instead of a bounding box, it's asking for the pixel locations for this object, and this object. So for the dog, it's determined that these pixel locations are responsible for the first dog, the green ones for the second dog, and the blue ones for the cat. And then there's another sort of maybe simpler approach to, or version of segmentation. Semantic segmentation which basically says for each pixel in the image, there's a classification problem. So, for example, for this particular image, there happens to only be grass, cat, tree, and sky pixels. But it wants to know for each pixel in the image, which of these is it? So that's what it's done. So here, the number of targets in the image is the number of pixels, and each target is categorical. Okay, so this is just to show you that even these variations on classification, there's a whole bunch of them. Okay, any question on any of these? So, yeah, so, I mean, it's very interesting how people have approached these problems. Generally speaking, the structure of the networks is not so different from what we have discussed. Of course, the number of outputs is no longer just 1,000 if you have 1,000 classes. It's a little bit more than that. But what's most interesting about designing these is choosing very sophisticated loss functions that somehow do the job you want to do. Somehow they're able to place these bounding boxes and so on. Okay, so now still with images, there's a whole bunch of other kinds of stuff you could try to do. So I'm sure you've all heard of JPEG image compression. It's when you take a picture with your cell phone and you save the file, it's probably not saving a file with 10 million numbers in it. It's doing some sort of compression, reduces the size by a factor of 10 or 100 or so. Well, those algorithms were designed, most of them in the 90s. The question is, can you design a deep network to do compression, better than those algorithms? And the answer is yes. There's a whole bunch of work on that. Then there's a whole bunch of work on removing artifacts from images. So if you have a noisy image, can you remove the noise while still keeping the image nice and sharp? Deblocking is if you have an image that's corrupted. Let's say you're watching television and you have a bad connection, and this is digital television, and all of a sudden you start to see these weird blocky artifacts. Can you design some processing modules in your television so that your television will clean those up and make it look, like it should, or at least make it look like you didn't even notice the blocking artifacts was there. So that's something you can do with neural networks. Deblurring, if you have some sort of blurry image, maybe, for whatever reason, the image got blurry, can you correct it? Can you make it sharp again? Yeah.
For something like image denoising, how do you get the model to return like an entire image?
Yeah, good question. So there's different architectures. The one that's closest to what we studied is an all convolutional network, but rather than kind of using max pooling or something to shrink the number of image pixels, it just keeps them the same as it goes through all the layers. It may expand the channels to like 16 or something, or 64. And then at the very end, it squashes them back down to 3 if it's color. But it's just convolutional layers all the way through. There might be 20 or so. That's one architecture. Another one is a UNet, which is a little bit more interesting. There's sort of different paths in parallel that have different resolutions, a little bit remnant of the wavelet transform. So yeah, there's various architectures. There's ResNets too that are popular here. So, but yeah, with the exception of that, for denoising, now you have to choose a loss, and the simplest loss is just like L2, or you can use L1, but there's definitely more sophisticated things you can do as well.
So then do you have to feed it like an example of like a denoised image so that it learns
Yeah. So the simplest version of denoising would be supervised denoising, where you have a big data set of clean, sharp images, and then you have, maybe you can add the noise yourself, or maybe it's just additive white Gaussian noise, maybe it's something more sophisticated where you try to mimic what's happening in a camera or whatever you're dealing with. And then you train the network just to remove the noise and give you the clean image. That'd be the simplest one. But there's more interesting problems where you assume you don't have access to any clean images, and you somehow want to still figure out how to denoise them. And that's so the supervised denoising is kind of like a solved problem. People aren't really working on that anymore. We have really good methods, but this unsupervised denoising is much more interesting, and that's something that people are still working on. Okay, good questions. Any other questions? Okay. So then there's other versions of image recovery that are similar in spirit, but a little bit more, maybe a little bit more interesting. Super resolution is the problem where you have a small image and you want to make it large. Now, if you did that just by interpolation, the large image would look kind of blurry. So you want to make it large and still really sharp. So how do you do that? Phase retrieval is something that shows up in a number of different applications where you do not have access to the phase. All you have is magnitude. Typically, this happens in the Fourier domain. And this happens quite a bit in optics. So in optics, lenses sort of do like a Fourier transform spatially. And if you want to build a microscope that can get really, really close to the thing you're imaging, you really want to try to find the thinnest lens possible. But even then, the lenses are too thick. So the question is, can you just get rid of a lens altogether and build a microscope without a lens or with a computational lens? And when you try to do that, you find that you cannot, you can build sensors that capture brightness, but they don't capture phase how you'd like. So you have to recover the phase computationally as well. So that's phase retrieval. It's also used, it was used to image the DNA helix and a bunch of other things. It also shows up if you do things like, I could use that wall as a mirror. What I would have to do is there's different ways to do it, but one way is to sort of train a system so that it learns how that wall behaves. And then once I know how that wall behaves, then I can have another system that knows how to use it as a mirror. And when you do that, you end up also facing these phase retrieval problems. Okay. Then we have applications in medical imaging like magnetic resonance imaging or computed tomography. So in magnetic resonance imaging, you capture the data in the Fourier domain, but because if you sampled at the Nyquist rate, meaning if you captured enough data that you could just do an inverse Fourier transform, it would take too long. The patient would be in the machine for too long. And so in modern scanners, they try to reduce the number of samples you take by a factor of 4 or 8 or so. And then essentially you have to try to use some sophisticated approach to make up for the missing data. Computed tomography is sort of similar. That technology is used quite a bit in the scanners at the airport that look inside your bags and stuff. In painting or image completion is if I would have this image and I would take out this part and you wouldn't see anything there, and then the goal would be to fill in what was there. So there are techniques that can do this remarkably well now. One application is if there was writing on an image and you want to get rid of the writing, you could just kind of block out all the pixels and then in-paint them, and it would look like they were never there. So these are all different things you can do with images. I'll talk about image generation in a couple more slides. And this is just imaging. There's way more applications outside imaging, of course, you can use deep networks for. As I mentioned before, in response to a question, the networks might look similar to what we've seen. You might have to adjust the number of outputs of the network. But then there's other interesting architectures. There's some architectures that are recurrent, kind of like if you studied DSP, they talk about infinite impulse response filters or recursive filters. It's very much the same, where the network takes in an input, but then it also takes in a previous output of the same network. And so those networks, recursive neural nets, were eventually replaced by something called long short-term memory networks. And those were eventually replaced by something called transformers. And transformers are non-convolutional networks. They're especially good at understanding context and where to look for information. And they are responsible for the revolution in natural language processing and chat GPT and all that stuff. That's all based on transformers. You can use transformers for images too, if you figure out a way to take image patches and represent them almost like words, and then put them through a transformer that sort of interprets them almost like it interprets words in a sentence. Okay, so any other questions on any of this stuff? All right. So let's talk about a few other kind of interesting structures that you'll find. Autoencoders. Autoencoders are, it's a pair of an encoder and decoder, both would be neural networks, where the encoder network tries to do some sort of compression. It tries to take the input and squeeze it down to a vector of, or a tensor or whatever, of much smaller dimension. And then the decoder tries to uncompress it, and it tries to make the output the same as the input here. So that's kind of the goal. There's various reasons why you might want to do this. Maybe you're just thinking about this like compression, so this is just your compressed image. Or maybe you're using this for denoising, because essentially most noise, you can't really compress it. It just, you can compress signals with redundancy, like natural signals like images, speech, audio, but noise, you can't really compress. So when you try to do this, what tends to happen is the noise gets filtered out. And what remains is the signal. You can also use this for anomaly detection. If you want to know, let's say you have one training data set, and someone gives you a new sample and says, is this sample typical of this data set, or is it an anomaly? Well, if you've trained one of these for a data set, then samples from that data set are reproduced well, but if you put in an anomaly, the output will be very different. So you can detect anomalies this way. Finally, it can be used for what's called generative modeling, which is to say, let me describe that for the variational autoencoders. So that's very similar to an autoencoder. You have an encoder network and a decoder network. But rather than the encoder producing a deterministic, what they call latent vector or code vector here, it actually produces a mean, here's the mean, a mean vector and a variance or standard deviation, such that if you generate a Gaussian random vector with this mean and this standard deviation and put it through the decoder, you should get an image very similar to this one. So that's what a variational autoencoder is. And these are useful for generative modeling, because once you've trained this, let's say you have this big data set of images and you put a cat through here. If you plug in different random vectors with the same statistics, you should get different cats. So that's an example of generative modeling, where you just want to generate many different things that are all structured in a particular way, all cats. The training cost typically looks like this. So here we have, this is a regular L2 norm, the difference between the input and the output of the generator. So here, or this is, sorry, the decoder. The decoder, you can see it has a mean plus this variance times, this is a pointwise multiply, times a Gaussian. This is a white Gaussian here. And then so we're looking at the expectation, so we're taking the expectation over all of these guys. So this part tries to make the input and output look similar. And this part tries to make it so that the mean and the variance that you're learning are close to zero mean and unit covariance. And the way that it does that is something called the KL distance, which is a distance between distributions. And so it's trying to say that this Gaussian distribution should be similar to this one in the KL distance. Okay, just an example of one training loss that's a little bit more interesting than some of the ones we've looked at. Okay, so that's autoencoders and VAEs. Any questions on those? Okay, so these were popular, I don't know, maybe like 2015 or so. And then they got sort of replaced by GANs. So GANs have a generator, which basically looks like this. The generator takes in a random, except it just takes in a random white Gaussian or zero mean unit covariance, identity covariance Gaussian, and you put it through the generator and it tries to recover samples similar to the ones from your data set. So for example, maybe I have a data set of faces and I want to train something to output random faces. So the ones it generates should not look like any of the ones it was trained with. They should be sufficiently different, but still, they should still look like faces. This is an example of what we call unsupervised learning because there's no targets here. So what we do is we want to design a generator that maps this latent vector, zero mean identity covariance Gaussian, to the image domain, in other words, like to the face domain. In order to do that, we designed it what's called a discriminator, which is another network. That's a classification network, and that classifies whether an input is either a real image from the training database or a fake one that was not from the training database. And we jointly train the two of them. So an analogy would be like if you have a counterfeiter trying to make fake money, that counterfeiter tries to be better and better at making fake money. Meanwhile, you have like law enforcement that's trying to catch counterfeiters. So that keeps getting better and better at noticing fake money, And as one gets better, the other get better. And they just keep training together until they're both quite good. So that's essentially how it's done. So there's a particular loss used for the generator, which could be the natural log of the discriminator. So this might be a real number output. And the discriminator sees the output of the generator. And then the discriminator itself has a loss, which is sort of like a binary classification loss. So there were various versions of this, progressively got better and better and better. So those are GANs. Any questions on these? Okay. Then a little bit more recently, we have normalizing flows. Normalizing flows are, again, similar in spirit to autoencoders. So here what you do is you have, except yeah, maybe it's a little bit misleading here. But these flows, they're invertible. So you build an invertible neural network. So because it's invertible, the input and output must match in dimension. And the objective of this network is to take things like, images from a class, a database of images like faces, and try to map those faces to unit variance or zero mean identity covariance Gaussians. So it tries to map faces to Gaussians. If it gets really good at that and it's invertible, then you can generate random Gaussians and map them backwards to faces. So that's the goal there. The advantages over GANs would be that they're simpler to train. You can train them using maximum likelihood. You don't need to have a discriminator. And the maximum likelihood loss looks like this. So here you have a Gaussian part. So this is your training samples. You put them backwards through the GAN to try to make them look Gaussian. So then your likelihood would have this Gaussian term, but it also has another term that has to do with it's the Jacobian, which is basically how the space got warped when you went backwards through that network. So this is, this is basically the likelihood, and this can be trained just with backpropagation. The catch is that both the network as well as this determinant of the Jacobian, both of those things must be easy to compute, which means it places some pretty severe constraints on how you build the architecture. So you have to have very special invertible layers, computationally efficient layers. Still, they've gotten really great results with these. I would say competitive with GANs. So that's getting pretty modern. Those were popular, maybe like 2 or 3 years ago. Most recently, for generative stuff, we have diffusion models. So diffusion models are similar in spirit to this idea, but rather than going in one step from image to Gaussian noise, you go multiple steps. So the way that this is written, it's flipped. So you start with an image, and you make it a little bit noisy, and then a little bit more noisy, and a little bit more noisy. And if you do this, let's say 1,000 times, you can get something that looks, very much like noise. So moving in this direction is easy. You just add a little bit of noise each time. So you can say the conditional probability of this, given that, is this Gaussian, where you have here, this is the new one, this is the previous image. You're just going to scale it a little bit, and you're going to add a little bit of noise. The trick then is, how do you go backwards? So once, can you then reverse the process? Can you take white noise and go backwards with a model that is using this distribution to go back in little steps to remove noise a little bit, until you get a clean image? So these models it seems like they have replaced flows and GANs and autoencoders as the most popular ones today. Other nice things you can do with these is you can bring in not just images, but other modalities like text. You can work with text and images together. And so this is where things like Stable Diffusion, DALL-E, Image Gen, various of these things this is the genesis of them. So for example, if you type in a sentence, or not a full sentence, just a description, then you can have it generate an image following that description. Or vice versa, you can give it an image and ask for that caption. caption for that image. And it's basically done. It trains a single network that you apply roughly 1,000 times or so to actually in this way. You start with a complete randomness, and then you gradually bring in structure, little by little. Or if you're starting with a caption, you would have a caption in randomness, and gradually you would get the image. Okay, so that's those are diffusion models. And there's links to all the main papers if you want to learn more. So that's all I have for this unit. Are there any questions about any of those last techniques? I'm just curious, how many of you guys have heard of diffusion models? Okay. How many of you have heard of GANs? Okay. What about autoencoders? All right. Okay. So, yeah, we don't have the time to get into the details of any of this stuff, but if you're interested, you can, click on links and learn more, maybe use them in your research if you're a grad student. All right, no questions then? Okay, so on Wednesday then, we have second midterm in this room, the usual lecture time. 2 note sheets are allowed. You can bring in the one from the first midterm and make a new one if you like. Are there any other questions regarding midterm? All right, so I'll see you guys on Wednesday.